Hello students, today we are going to discuss the use of Z as a sampling distribution for differences between two sample means. With the help of the same, we can come up with the formula for 1 minus alpha percent confidence interval for the differences between two populations. Now let's start with the concept that we have discussed in case of one population. This was the formula for Z that we have used. And from this formula, we have come up with the 1 minus alpha percent confidence interval formula for estimating one population mean like this. Now, moving from one population, we know that we will have two different populations. Their population sizes would be n1 and n2 respectively. The population means we may be getting from population 1 and population 2 would be mu1 and mu2 respectively. The population standard deviations or variances would be sigma 1 square and sigma 2 square or sigma 1 and sigma 2 respectively. Now what if we draw sample size of n1 from population 1 and sample size of n2 from population 2? That would definitely give us the sample mean value of x1 bar from the first sample data and x2 bar from the sample data obtained from population 2. Now, we will get, instead of, if we would like to connect with this formula, the description. So x bar would be splitting up into two, x1 bar and x2 bar, and we will connect these two sample means in the form of difference. Similarly, the second factor, which is mu, would again split up into two factors following the same rule, that is taking the difference between the two. Then if we come up with sigma divided by root n, that can be alternatively written down as sigma square divided by n inside the square root sign, and this would split up into two factors, that is the standard error taken out from sample data 1 and standard error taken out from sample data 2. So this is how we can get this formula transformed in this way. So x1 x bar can be rewritten as x1 bar minus x2 bar. Mu can be rewritten as mu1 minus mu2. And in place of standard error of single population, we can get this replaced with sigma 1 square upon n1 plus sigma 2 square upon n2. Now recalling how did we derive this formula that I am going to denote as 1. What we did over there, first of all, we have assumed regarding the behavior of our random variable x that random variable x follows normal distribution with some mean mu and some variance sigma square. And then we have defined this formula as that random variable x bar we are dealing with. So this is mu of x bar and this should be sigma of x bar. Alternatively, we can write it down as x bar minus expected value of x bar divided by square root of variance of x bar. It's the same thing. Standard error is in fact the square root of the variance of x bar. Now, since we are now dealing with two different population data sets, so regarding both, we need to take the same assumption that x1, random variable x1, is normally distributed with mean mu1 and variance sigma 1 square, whereas random variable x2 is normally distributed with mean mu2 and variance sigma 2 square. Now, if our random variable we write down in this way that it is the difference between the two sample means, then following the same structure, we need to write this down as expected value of x1 bar minus x2 bar, and then in the divisor or denominator we need to write down that this is square root of the variance of x1 bar minus x2 bar. Now, considering this factor A, what we can do, expected value of x1 bar minus x2 bar can be written down as summation x1 added up to n1 terms divided by n1. So what I have done, I've just written down the formula for x1 bar. Similarly, this is the negative sign or minus sign between the two terms. We can write down this as well, the second term. Now applying expected value operator inside the parenthesis or bracket, this expected value operator will only be applied on variable x1 and summation comes outside. Similarly, on the second term as well, this expected value will be applied on x2 divided by n2. Now we have described that this is referring expected value of random variable x1, and this is representing expected value of random variable x2, which are mu1 and mu2 respectively. So what we do, added up to n1 terms, we can write down in place of x expected value x1 mu1, and similarly in place of expected value of x2 we can write down mu2. Now we can read this mu1 applied summation sign on that. We can read it as mu1 is added n1 times, and we can alternatively write it down as n1 mu1 divided by n1, and similarly we can read the second factor of the numerator as mu2 is added n2 times. So we can write down in its place this thing. These two will be cancelled out, these two will be cancelled out, and ultimately we get mu1 minus mu2 as the answer to expected value of x1 bar minus x2 bar, and this is what we can write down over here in place of x1 bar minus x2 bar. Now applying the same thing and working out the variance or the result for the variance of x1 bar minus x2 bar, again this can be written down as n1, this minus sign that is between x1 bar and x2 bar we can take out as common factor or make it separate. Similarly, This is how we can write it down, because we know the property of variance operator. Whenever variance is applied on a constant quantity, it will become square. So there are three constants involved inside this bracket: n1, minus 1, and n2. When we apply this variance operator on these three factors, we get it all changed to square. Now, and this variance operator will be only applied on variable. So n1 variance of x1 divided by n1 square. This minus 1 will become plus 1 when variance operator is applied on this minus 1 factor, because it will be make it squared, and minus 1 squared is plus 1. So we change the sign to plus. Similarly, here variance operator will be applied on x2, and variance operator, when it is applied on n2, it will become n2 square. Now variance of x1 and variance of x2 are these two. This is variance of x1, which is equal to sigma 1 square, and this is variance of x2, which is equal to sigma 2 square. So over here we will write down their values: sigma 1 square upon n1 square plus summation sigma 2 square added up to n2 terms divided by n2 square. Now this can be read as sigma 1 square is added n1 times, so we can write it down in this way, and consequently this squared exponent will be cancelled out with one term given in the numerator. Second term will be changed in the same way, because this we can read as sigma 2 square is added n2 times, and this can be rewritten as this. And similarly, the square of divisor denominator will be cancelled out with the numerator factor, and we get sigma 1 square divided by n1 plus sigma 2 square divided by n2, and this is the answer to variance of x1 bar minus x2 bar. Now substituting here the value of this, we need to take square root, and when we apply square root on both the sides, sigma 1 sigma of x1 bar minus x2 bar would be equal to the square root of sigma 1 square on n1 plus sigma 2 square on n2. This is what the result we get. So A, I've labeled this formula as, this factor is B, and their values are this and this. So we can plug in the formula, and this is how we get this formula. That's for the use of Z as a sampling distribution for the difference between two means. Now we are going to apply, in the next video we are going to apply this formula in the sampling distribution on a specific data set.